Okay, folks, welcome to the next lecture. And in this lecture, we're going to take a look at exponential functions, just an introduction, and we'll take a look at solving some exponential problems. So, how do we recognize an exponential function? This is very important. Up till now, we've been looking at kind of functions where we had linear functions, we had quadratic, we had cubic, we had reciprocal functions. In all of these functions, the variable is the base, and then the power is what determines the nature of the function. With an exponential function, it's the base is actually fixed, but it's the power is where the variable lies. So our input is a power. Up till now, we've generally been looking at where the input is the base and then the number on the power determines the nature of the function. So this is a very important distinction. So anywhere where you see your input as a power, you're dealing with an exponential function. So these are all examples of exponential functions. Sometimes people think that the letter E is an exponential function, e to the power of. Now, e certainly is. Any function with e is exponential because by its nature, e always has the input as a power. So by definition, the value e is an exponential function, but sometimes people think the e actually stands for exponential, which it doesn't. It's just one of the e. This function is just one of the number of members of the family of exponential functions. But it always is exponential by its nature. We'll examine e, what it is, where it comes from in this lecture. Here's the simplest function. And then here's the general function. We'll be using this a lot in the next lecture when we start looking at growth and decay functions, which are very important in science. Quick recap where we are. Here's our functions up to now. Like I was saying, up till now, the base was our input was the base, and then the number on the power defined its nature, certainly for these first four functions. We looked at trig functions, we looked at log functions, and now we're looking at exponential functions. Later then, we'll determine the nature of functions, and we'll also look at calculus. So the power is first of all essential with exponential functions, and more importantly, the sign on the power. If the power is positive, it's a growth function. If the power is negative, it's a decay function. And as I said, we look at these functions, growth and decay, in a lot more detail in the next two lectures. Here's the natural log function and its inverse function. If we plot it, so these are inverse functions. They cancel each other out, and there's a very simple symmetry between them. We'll be using this later on, but just to have a look at the graph, that there is this symmetry between y is equal to e to the power of x and y is equal to the natural log of x. Now what we're going to do is, just before we start defining the exponential function proper, we're just going to have to introduce the idea of a limit. And one of the best ways of doing this is going back to ancient times and looking at Zeno's paradox. So Zeno's paradox says a soldier is to leave city A and he's to travel to another city B, which is 100 kilometers away. Each day he travels half the remaining distance. So the question is, how long will it take him to get to the second city? So here's city A, it's 100 kilometers to city B. So each day he travels half the remaining distance. So when he leaves on day one, he has to travel 100 kilometers. And at the end of day one, he's travelled half of that distance. So the next day he wakes up, he's got 50 kilometers to go, so he travels half of that distance. Next day he wakes up, he's got 25 kilometers to go, so he travels the following day, he'll only travel half the distance. And so it goes on. And the question that's asked then is, how long will it take him to get to the other city? The answer is he'll never actually get there, although he will get infinitely close to city B. So say after 300 days he's only got a centimetre left to go, well, the next day he's only going to travel half a centimetre, so he'll still never reach there. Say another 100 days later he's only a nanometre away from city B. The next day he's only going to travel half a nanometre. And it continues. The gap between him and the city gets infinitely small, but he can never reach it. And this is Zeno's paradox then. If we try and represent this mathematically, we start to kind of define what's known as a limit. So this is his journey now. It's a bit roughly drawn out, but essentially, as time goes by, he gets closer and closer to a fixed value, which in this case is 100 kilometers. So as time goes by, this thick line will get closer and closer and closer to 100 kilometers, but he'll never get there. So what we would say in this case, that 100 kilometers is the limit of this function. So the curve will get infinitely closer as x gets bigger and bigger. The value of y gets closer and closer to this limit, but it'll never get there. And we're going to use this concept of a limit now as we go on to define E, Euler's number. First of all, we're just going to kind of show where the number, the value of E comes from. So I've just kind of invented this example of a bank. So a bank has joined, Poxy Bank has joined the online market. And if you borrow €1, the bank offers a rate of 100% over a 1-year term. So you'd expect, you borrow €1, at the end of the year, you'd expect to pay back your loan of €1 and you'd be expected to pay back 100%. So you'd think you'd have to pay back €2 at the end of the year. Because of their name, though, there's buried in the small print is a clause that Poxy Bank, they can decide how often you pay back your increments. So they could say, okay, one payment of 100% at the end of the year. So that in that case, you'd pay back your €2. We'll look at all the maths of this on the next slide. Or they could say you need to make 2 payments of 50% every 6 months. So the 2 by 50 adds to 100, but it doesn't really. You could pay 4 payments of a quarter, 25% every quarter. 12 payments of 8.33%, so 12 by 8.3 gives us our 100%. So each time Poxy are just, if we multiply those values, we always end up with 100, but there's some clever kind of accounting going on. We could pay back 1.92% every week. 365 payments of 0.264 every day. We could be asked to pay it back every hour, or even every minute, or even every second. So this is how many seconds there is in a year. So Poxy, they get to decide how you pay things back. They can structure that 100% any way they want. Now, if we start to take a look at the maths of this, we'll see that kind of Poxy Bank can get considerably more than the €2 repayment. If they just went, this simplest option is the best for you, but it's the worst for the bank. This option down here, as we'll see, is the best for the bank and worst for you. But what we'll see is, no matter how finely they start splitting up the time intervals, there is a limit as to how much you will have to pay them back. So we'll take a look at the maths of all these repayments now on the next slide. So if they pay back once a year, then you'll end up paying €2. If you pay twice a year, you'll end up paying €2.25. Pay back 4 times a year, you'll pay back €2.44. 12 times a year, you need to pay them back €2.61 over the year. And we can see that the value is increasing, but as we go along, the gains that the bank can make are limited. And what we say is there's a limit. There's a limit to how much the bank can get back, and it's this value here. Now, if this goes on, we could start dividing up things into milliseconds, nanoseconds, and really drive it further and further. But there will be no financial gain for the bank to do that. And this is why banks generally go for monthly repayments. They get most of the benefit, but they don't have to incur the cost of applying this maths. There's not a whole lot of gain to be had by making the divisions any smaller than a month. So this figure is what actually becomes, this figure now is the limit as to how much you'd have to pay back. And obviously we could drive it further and further, but it's just going to get closer and closer to this limiting value. And this is kind of the basis of the natural exponential function, e to the power of x. And what this function is actually trying to do is it's trying to mimic natural growth. Natural growth occurs continuously. It's not something that every year, say you were growing 6 inches as a kid. It's not like just on your 4th birthday you suddenly spring up 6 inches. The 6 inches growth you'd occur over a year would be kind of incremental. So that's what this function is trying to define, is this idea of continuous growth. And I'll talk about pi very briefly, but pi is another function. Pi is called a transcendental function. And how you get pi, it's the circumference of a circle divided by its diameter. That's what gives us pi. Circumference over diameter is pi. Now pi is used anywhere where you have any circle. If you remember, the circumference of a circle is 2 pi r. Radius, area of a circle, pi r squared. Volume of a sphere, 4 over 3 pi r cubed. Surface area of a circle, of a sphere. So anywhere where we have anything round, pi is always involved in that calculation. If we're looking at speed of rotation, pi will be in there as well. So anywhere where you have circles or circular motion or anything round, pi will be involved. In the same way, anytime we have natural growth or natural decay, which as scientists is what we study all the time, how the human body behaves is really a study of growth or decay, natural growth, natural decay, any environmental study. An awful lot of work that scientists do is governed by this function, e to the power of x. So just like I said, anywhere where you have something round, pi is the boss. Anywhere where you have natural growth or natural decay, if I draw these as a graph, then these are governed by this function e. Sorry, that's just a little bit, that's moved off a wee bit. So that should just simply be, sorry guys, that's just moved a wee bit on the slideshow. Y is equal to e to the power of x is used to describe natural functions. So e doesn't stand for exponential. It's actually called Euler's number. And the e isn't a thing of vanity. He didn't pick e because it's the first letter of his name. It was actually, he was trying to find a function with a limit on it. And this was the 4th attempt. Or the 5th attempt, sorry. So the first 4 attempts were called A, B, C, D. And the 5th attempt, in which he achieved what he was looking for, was called E, and that's why he called it E. So it's a very simple reason. It's not for vain reasons. E doesn't stand for exponential. A lot of people think that. It's not. Exponential, any value can be exponential. So this is an exponential function because our input is a power. So this is the function that Euler used to develop this value. And this is a function which represents continual incremental growth. And continual incremental growth is the definition of natural growth. Then he was looking for the limit. Well, as this function grows, just like with Zeno's paradox, as the soldier moves from city A to B, what's the limit? What value is he going to get very, very close to but not actually reach? And in this case, the limit is, as we saw, 2.7 whatever. So here we have the function. As n gets bigger and bigger and bigger, this is n here, the value of this gets closer and closer to this value here, 2.71828182846. Goes on forever and ever, just like pi. So you can't define this value without rounding it. Goes on for infinity without repetition. That's the nature of a transcendental number. So that, guys, is what E is. It's simply a value, and just the way as pi is 3.14 and it's got loads of different values, that's all this number is. It's used to describe natural growth or decay, depending on the sign on the power. This is its formal kind of mathematical inscription. It's the formal definition of E. And like I said, this is it written out to about, 15 decimal places. It goes on forever and ever though. So E is the base of primary interest to natural scientists, as any system which grows or shrinks naturally is governed by this. Computer scientists, they use 2 as their base of primary interest, as microprocessors are governed by the binary system. Everything is either a 1 or a 0 in microprocessors. So they use a base of 2, whereas we're scientists, we're generally interested in natural systems, so we use E as our base. Metric system, centi, deci, milli, kilo, mega, giga, they're all governed by the base of 10, and that's why we also study logs as well, because that's log to the base 10. So they're as scientists, the 2 bases we're particularly interested in are these 2. Now, we studied logs in the previous lecture, so I won't go back into them. And as I said in the last slide, E is a transcendental number. It's similar to pi. So that's the basis of this value E. But the one thing to recognize, guys, is it's just a number. It's simply a very important number to natural scientists. But other than that, it's simply just a number. So we'll just take a look at an exponential function at work, and we look at this spread betting program. So this was a friend of mine introduced this to me years ago, and I always kind of remember it. He kind of came running. He was my flatmate, and he came running downstairs and he said, come on, we need to buy this program. They're offering, if we pay them 10 grand, they can guarantee you'd get a 1% return on a spread. So what a spread would be is, say if Liverpool were playing Man United, Liverpool versus Man United. With spread betting, what you would actually do is bet on all the possible outcomes. You would bet on Liverpool winning, you would bet on Man United winning, and you would also bet on it being a draw. And this program would go kind of around the world to different bookies, and it would ensure that regardless of what happened, you would come out with at least a 1% margin. So you would always win at least 1%. But obviously you're going to lose 2 bets. You'd have to bet on all 3 outcomes, so you're always going to lose 2 bets. But the idea is that your winning bet would outweigh your losing bets. So a 1% daily return of 1% on €1,000. That's what we're going to take a look at. So what would his investment be after one day? well, then he'd get 1% of 1,000, which is €10. So at the end of one day, he'd have 1,010 euros. 5 days. So we look at these in the next slide. And this just gives you an idea of how an exponential function grows. They just grow very, very quickly. There's always a slow start to them, but then they grow very quickly. So this is just a function that calculates the return. Here's the 1% return. Here's our money. We always want to make sure we get our money back. And this is the number of days. Here we have the 1,000 euros of the initial bet. So after 1 day, he'd have this much money. After 5 days, be 51. You're like, yeah, 5 by 10, that's about right. 30 days. Now you're going, okay, the money is getting good. 100 days. We've more than doubled our money, nearly tripled it. After a year, sorry, it's going a little bit out of sync. We'd have nearly 40,000. So for €1,000 bet, you'd now have close to 40,000. After 2 years, we'd have nearly 1.5 million. Now, it's not that simple. Like you're probably asking, why am I still here teaching maths? Basically, it's very hard to lay out 1.5 million every day in bets. Bookies just don't allow it happen. So obviously bookies are aware of these things as well, and they make sure that they're not going to lose. The bookie always wins, and if you believe otherwise, you're going to part with your money very quickly. So I'm not going to develop this example anymore, guys, but it just shows this slow start, but then it accelerates very, very quickly. Because each day, like at the end of day one, the person has to lay off all his money again. So each day you're having to lay off all the money to get your 1% return. So at the end of this day, this person is going to have to lay out the next day. Say he won this much money on a Monday. On a Tuesday, he's going to have to sit down at his computer and spread out 1.4 million across 3 bets, which, as you can imagine, is obviously going to raise some eyebrows. So it's a great system mathematically, but in the real world it doesn't work like that. But it's a nice example to give you the idea of how exponential functions grow. Slow at the start, but then they grow very, very quickly. And you see this with the current situation with COVID and stuff like that. So now we're going to take a look at solving exponential functions. So logs. So up till now we've been looking at inverse functions. Plus and minus are an inverse function. They undo each other. Multiplied and divide are inverse functions. Squared and square root are inverse functions. They undo each other's actions. If we want to kill a base, we use a log. So we were looking at that last week, and now we're just going to look at e as a base. And if we want to remove the function e, we use log to the base e. So this is what we're going to be doing now in the following examples, is just solving exponential functions. And these functions will invariably involve e, because as I said, as scientists, these are the ones we're typically most interested in. So we take a look. Solve the following exponential equation, not equations. So here, guys, we have two things. We want to get x on its own. We always want to work from the outside in. So the first thing we're going to do is remove the 2. And then we're going to remove the e. Don't try and kill the e first. You must work from the outside in. So 2 is joined on by multiplication. Our first step is to divide both sides by 2. Now you can work this out on the calculator, because dividing by 2 will always give you, there's no rounding involved. So when we do that, this will give us 3.24. So I'll divide both sides by 2. So I could just write that as 3.24. Now next I want to get rid of the e. So how do I do that? I get log to the base e of both sides, and remember log to the base e is very often called ln. So we get the natural log of both sides. So when we get the natural log of the left, they cancel each other out, and then we'll get the natural log of the right. So when we get the natural log of the left, like I said, the e just cancels out. You don't need to write the intermediate step. So now we've got x is the natural log of 3.24. So you just get your calculator and work it out to however many decimal places is defined. We look at another example. This is similar. Again, we need to work our way, first of all, get rid of the 2, then get rid of the e, and then the minus 3. To get rid of the 2, divide both sides by 2. Now we want to get rid of the e, so we get the natural log of both sides. That kills the e, the minus 3x just drops down. And finally, we now want to get rid of the minus 3, joined on by multiplication. So we divide both sides by minus 3. Sorry, I shouldn't have deleted all of that. Divide by 2, get the natural log, then divide by minus 3. And now, and again, it's always best practice to try and keep the calculation. Don't keep diving for the calculator at each step, because each time you're going to introduce rounding errors. So now when we divide both sides by minus 3, we just get our calculator now and work out our answer. Here's another example, a little bit more complex. Now, first thing we have to get rid of in this case is the e. Then the minus 2 because it's the furthest away from x, and then the 4. So remember, you always work from the outside in. So he's first, second, and then the third thing to go. So to get rid of the base of e, get the natural log of both sides. Now we want to move this 2 across. We add 2 to both sides. And finally then, we divide both sides by 4. And when we get our calculator, we get x is equal to 1.19. A little bit more complicated example. This one often confuses people, and the first step people often take is to try and get the natural log of both sides, but you can't do that because there's 2 e's involved. The first thing we do is we actually use our rules of powers. If I said to you 2 to the power of 3 multiplied by 2 to the power of 2, I hope you'd agree, that this would now give us 2 to the power of 5. When we have the same base and they've been multiplied, we can simply add the powers. So that's our first job. We will add the powers. So we just add the x terms and we add the number terms. And now we're in more familiar territory. We only have one e term to deal with. That's going to be the first to go, then the 1, and then the 5. So to get rid of the e, we get the natural log of both sides. The power drops down. Now we're going to bring the 1 over. We subtract 1 from both sides. And finally then we have 5x is equal to this. We want to get rid of the 5. It's joined on by multiplication. We divide both sides by 5. And again, strongly recommend that you leave the calculator until the very last step. And when we calculate this out, this is our answer. So now, you know the drill. Here's some for you to try. Just give each of these a go. They're done in the exact same way as we just did in the previous example. So that kind of covers it for the first lecture, guys. In the following lecture now, we'll look at exponential growth, and in the lecture after that then, we'll look at exponential decay. So thanks for listening, and we'll chat to you soon.